Starting chapter 2. This is really simple. If you did okay in Algebra 1, you'll do okay here. But I want you to be aware of the homework assignment for tonight is rather daunting. Okay? So I would recommend spreading it out over the next 2 days so that when you come to class on Wednesday, you're ready to go. Okay? So there are a whole 2 problems. So figure out how you want to do that. You know, it could take a while. Two questions.
How many parts?
Yeah.
Question.
74 from each part.
That sounds about right.
It's really simple. Okay, so we're going to talk a little bit about tangent lines, and we're going to relate that to velocity, so we get a little bit of physics going on here. And this starts our true calculus. Oh, that should be chapter 2-1. Anyways, so this is the point where I say, okay, I don't know what you did in pre-calc last year. I don't know how good you are at pre-calc, but none of that matters now. Yeah, she's here. Thank you. None of that matters now because we're all starting with calculus. Okay? And the first concept is very simple. So we're going to calculate the slope of a line, which I assume you can all do, yes?
Yes.
Stay here all day. Okay. We'll talk about a secant line and a tangent line. You may have had a little bit of that last year. Maybe not. It's okay. We're going to calculate a slope. And we're going to talk about instantaneous versus average velocity. So, as I was saying, 3 topics in calculus. That's it. This is the first one, limits. Then we do derivatives. Then we do integrals. Nothing else. Everything else that we do is part of those first 3. This first part of limits won't take us very long. And it's not that bad. It's quite manageable. And in fact, derivatives and integrals aren't that bad. It's when you get into the nitty-gritty that things get a little bit crazy. And then you should be able to fit 20 grapes in your mouth without choking. Okay. Just for practice, and just to make sure we're all on the same page, could you please calculate the slope of line AB and the slope of line PQ?
Yes, we are. It's gonna be a nice, relaxing test there.
Olympic out there.
We got so many coming in.
Oh, that's becoming a distraction. Just trust me when I say it's bad out there. Andrew, what's the slope of AB?
Negative 3/4. Negative 3/4.
Can somebody confirm negative 3/4? Yes? We have one confirmation, we're moving forward. Any disagreement? Some of you look confused. That's okay, you can criticize, you'll be a skeptic. You're not criticizing Andrew, you're criticizing his answers. But you're good, 3/4? How long were we going to wait before, why, were you afraid of hurting his feelings? Andrew, are you upset by this? Do you need to see your counselor, or are you okay?
I need to see my counselor.
You're going to see your counselor. Okay, but maybe there's a therapy dog down there you can back for a while. 12 minus 4 is 8. Negative 5 minus negative 2 is negative 4. 12 divided by 4. Oh, wait, am I doing my math wrong? 8 over negative 4 is negative 2. Gamble, what's the slope of line PQ? Standing in front of the air conditioner. Undefined, beautiful. So what does that tell you about the line PQ? Is it this, or is it this? This will work well in the video too. Is it horizontal, or is it vertical? Is it horizontal or is it vertical? I can't hear you back here.
Vertical.
Oh, it's vertical. Very good. Yeah. Zero denominator, which means the x values are the same, so it's a vertical line. You have a question? Oh, you're just showing me vertical. Okay, thank you very much. All right, we're good with that? Good, Algebra 1 stuff. Let me explain what's going on in this picture. The purple curve is my function. Let's call it f of x. And I've got a point A on that curve. I also have a point B on that curve. And therefore, I drew a line, this one happens to be green, through the points A and B. That green line is called a secant line. It is a line that intersects a function in at least 2 points. Could be 3, could be 5, could be 12, but at least 2. The blue line, I took a point outside the graph, or off the graph I should say, and I drew a line through there. This one happens to be horizontal. That would be a tangent line. Now you're saying to yourself, hold on, it intersects over there on the left. I see that. He just didn't label it. Are we going to pretend that doesn't exist? And the answer is yes. Because we're looking at only the region around the point A. A is our focus. And we're going to go a small distance away from A. The blue line is what's called a tangent line. Intersects a graph in exactly 1 point. Everybody good so far? Good. But it's not rocket science. Now, we get a cool little demo. So before I show you the demo, let me ask you a question. What happens if B starts moving closer to A?
Slope of the secant line changes.
Excellent. You got anything else? That is true, it will change. That's okay, that's why we're learning. Hopefully this works. Bingo. It did work, beautiful. Okay, similar scenario. Instead of the points A and B, I have a point P and I have a point Q. Notice that the green line is my secant line. The red line is the tangent line. So let's talk about some terminology here. One of the things that we do in calculus all the time is we moved from x comma y to x comma f of x. So the point P is at the location x comma f of x. You're used to that notation, I hope, yes? Okay, good. And then I said from x, I'm going to move over a little bit. How far did I move over? I called that thing delta x. Remember, delta means change. Change in x. So I moved to the right. Could move to the left. It was easier to move to the right. So this new x value over here, that little green dot there, is what's called x plus delta x. Everybody with me so far? To find q, it becomes a replacement thing. We've done this already. What is f of smiley face? Go to the function wherever you see an x, put in a smiley face. What is f of x plus delta x? Go to the function wherever you see an x, put in an x plus delta x, which gives me that. Are we good to go so far with the setup? Any questions? Okay, beautiful. Now the next question is, which I asked on the last slide, what happens when q moves closer to p? Other than the fact that the slope of q will change, which we can see that. I think I can do this. Yeah. You see the slope of that green line change as it moves closer. Okay. What else is changing?
Delta x.
Delta x. Right. So as q gets closer to p, delta x is getting smaller. How small do we want it? Well, we want it really small. Smaller, 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 slowing down for some reason. Smaller, smaller, smaller. Getting closer. Smaller, smaller, smaller. Taking longer than I expected. Maybe I should have moved q closer. This is one of those awkward moments. And we're done. Okay. What can you tell me about delta x now? It's 0, correct. So we slid Q over to the point that it matched P. And when it matches P, then we've let delta x go down to 0. Are we good so far? That process is what's called a limit. We're going to do a lot of that. Let's go back to the slideshow. No. That equation, which may look familiar to you, you may know it as a plus h, so f of a plus h minus f of a all over h. It's the same formula, is the difference quotient. It's called the difference quotient. What is that value? That's the value of the slope of the secant line. Okay, so if I go back to this guy, that secant line slope is going to be y2 minus y1 over x2 minus x1. This is x comma f of x. This is x plus delta x over f of x plus delta x. y2 minus y1 over x2 minus x1 gives us that. That's not calculus, that's just algebra 1, calculating the slope with some fancy smancy notation. It becomes calculus when we start saying, okay, what happens if we make delta x really, really small? And in fact, we make it so slow we get to 0. That's in the next section. Right now, we just need to get the terminology under control. Question so far? Does it make sense? Okay, good. So there it is back to this. Now, this offers a different scenario. What if I want to know the slope of the blue line? You don't know how to calculate the slope of a tangent line yet. So what we can do is approximate the slope of the tangent line by choosing 2 other points. So C is the point I'm concerned about. I chose 2 other points, A and B. Now the weird thing about this is there's 3 different ways to do this approximation. I have one shown already. I can approximate the slope of the blue line by calculating the slope of the secant line between the point on the left and the point on the right. If you look at this picture, that answer looks pretty good. That's number 1. Number 2, I could choose to go through C and B. Wow. Imagine that line was straight. That would be an approximation for the slope of C by going through C and B. And then the other option would be to go through A or C. Now, when you look at A through C, that red line doesn't look anything like the blue line. And in fact, the black one's not that close either. So to answer my own question, how accurate is it? Not very good. How do I get a more accurate answer? Where can I move A and B to get a more accurate answer of the slope of the blue line? Here you go.
Closer to C.
Beautiful. One of them? Both of them?
Both.
Both. Good. How close?
Practically like on the point, like right next to it.
Beautiful. You just summed up calculus in a statement. Okay, one of the things that makes us this calculus and not algebra 2 or algebra 1 is the fact that we're going to move B and A really, really close to C. How close? So close that it's infinitely close to the value for C, and that will eventually give us the values. Okay? And that's the gist of what a limit is, which we'll get to in the second section. Okay, let's have a quick discussion about a trip to Grandma's house. Let's suppose your grandma lives in Madison, Wisconsin. Anybody's grandma live in Madison, Wisconsin? That would have been weird. Okay, you get in your car, you drive to Grandma's house, you leave your house at 9 a.m., you get to Grandma's house at noon. Approximately, what is your average velocity? It's not a trick question. What's the speed limit on the highway?
65, you're going slow.
We'll be law-abiding citizens and we'll go with 65 miles per hour. Okay, that's your average velocity. It would actually probably be a little bit lower, but everybody okay with the average velocity? Okay. How does the average velocity in your trip to grandma's house differ from the instantaneous velocity? Are you ever doing 65 miles per hour on the way to grandma's house? Yeah, at some point you are. Are you always doing 65 miles per hour? No, you're not backing out of your driveway at 65 miles per hour. You're not barreling through the drive-through at Belvedere Oasis at 65 miles an hour. Your speed fluctuates. But when you take all the speed that you traveled from your house to grandma's house, the average velocity is just that, the average velocity over time. Instantaneous velocity is the time at any given point in time. So when you get in the car in your driveway, your instantaneous velocity is 0. When you're driving down your street in your neighborhood, your instantaneous velocity is probably 25, 30 miles an hour, depending on where you live. When you're out on the highway, it's 65, 70, 75, 80, depending on how big of a psycho driver you are. Okay. Remind me when I stop recording, I got a good story for you about psycho drivers. You understand the difference? From a mathematical standpoint, average velocity equates to the slope of the secant line. Instantaneous velocity equates to the slope of the tangent line. And we'll practice that a little bit more when we get into tangents. Okay. We good? We're done. Told you it would be quick. Any problems? Good.